NGC 6543. The Cat's Eye Nebula, a layered shell of fading light. As the universe exhales in slow, luminous breaths, there are places where matter becomes memory, where stars, having spent their fuel and fury, begin to shed their outer layers like ancient trees losing bark, revealing inner histories in spirals and rings of soft, expanding light. One such place is NGC 6543, more poetically known as the Cat's Eye Nebula. Nestled within the northern constellation of Draco, it lies more than 3,000 light-years away, yet its presence is unmistakably vivid even from that immense distance. It does not simply mark the end of a star's life. It memorializes it in concentric waves of color and structure that ripple through the surrounding void like the wake of a celestial sigh. The Cat's Eye Nebula is not merely a single burst or a simple remnant. It is a cosmic palimpsest, a record of many epochs written atop one another in loops and filaments of ionized gas. Its central star, once stable and fusion-fed, exhausted its core hydrogen long ago. Like many sun-like stars, it ballooned into a red giant, pulsating with instability as it began to lose its grip on its own envelope. Over time, this once coherent star expelled massive shells of gas, layer by shimmering layer, as though the star itself had become overwhelmed by its own gravity and light. These shells are what we now see as the nebula, a series of nested, glowing rings that form an almost crystalline complexity in the sky. Ultraviolet radiation from the dying core continues to excite these expanding gases, causing them to fluoresce with eerie blues and greens, revealing oxygen, hydrogen, and nitrogen in luminous detail. The result is a three-dimensional sculpture formed not by human hands, but by pressure, plasma, and time. A structure that is at once beautiful and foreboding. A reminder that all stars must eventually release what they once held. Yet NGC 6543 is not only striking in its form, it is scientifically profound. It was one of the first planetary nebulae ever observed in high resolution by the Hubble Space Telescope, and what it revealed challenged prior assumptions. Astronomers had long believed planetary nebulae formed relatively simple, spherical shapes as their stars died. But the Cat's Eye shattered that simplicity. It is intricate, asymmetric, marked by high-velocity knots, twisted jets, and multiple envelopes of material, proof of chaotic internal processes. This complexity suggests the involvement of binary dynamics, where a second, unseen companion star might have tugged and twisted the gas clouds into spirals and helixes, choreographing a cosmic dance in which death itself moves with elegance. This nebula is also a time capsule. Each concentric ring represents an earlier chapter in the life of the central star. Some estimates suggest that these rings were ejected in regular intervals, every 1,500 years or so, offering a rare glimpse into the rhythmic dying pulses of a star. It's as if the star, in its final centuries, had begun to breathe in light and exhale in color. Each breath slower than the last, each ring a whisper that drifted into interstellar space. The light we now receive from NGC 6533 began its journey toward Earth before the rise of human civilization as we know it. When that light first departed the nebula, no pyramids yet stood in Egypt, and no wheel had turned on Sumerian soil. Yet here it is now, washed onto our telescopes, captured in our instruments, and etched into the collective memory of modern astronomy. But perhaps what makes the cat's eye most haunting is that its spectacle is not eternal. The rings that now glow will cool and dissipate over tens of thousands of years, becoming more diffuse with each passing millennium. The central white dwarf at its heart, once a master of fusion, will dim steadily, cooling into a black dwarf over unimaginable spans of time. Eventually, all that will remain of this once vibrant system will be dark, quiet atoms, drifting anonymously through the Milky Way. In the cosmic interplay of density and dissolution, NG 6543 stands as a luminous echo, a place where creation and disintegration exist not as opposites, but as stages of the same unfolding narrative. It is a frozen breath in space, captured between the moment a star lets go and the instant it vanishes into the silence. And as we stare back across the light years, we are not merely observers of its fading glow, we are its witnesses, its archivists, and perhaps its last audience before its light becomes dust. In the long twilight of dying stars, like that which formed the Cat's Eye Nebula, we witness the graceful end of stellar life. But for every celestial object unraveling into silence, there are others rising quietly into potential. Somewhere beyond the fading shimmer of NGC 6543, across the steady arms of the Milky Way, a small red sun burns with the dull persistence of youth. Around it orbits a planet that has captured both scientific curiosity and a deep, almost instinctive human longing. This world is Gliese 832c, a super-Earth orbiting within the habitable zone of a star barely visible to the unaided eye, yet radiant with possibility. Located just over 16 light-years from Earth in the constellation Grus, Gliese 832c is one of the closest potentially Earth-like planets known to science. It circles its parent star, a red dwarf called Gliese 832, which is smaller and cooler than our own Sun. Despite the star's relative faintness, the planet's tight orbit places it squarely within a region where liquid water could, under the right conditions, exist on the surface. That simple fact propels Gliese 832c beyond the realm of theory into the beating heart of planetary science, astrobiology, and the quiet search for a second Earth. The term super-Earth does not imply similarity to our world in every aspect. It refers primarily to mass. Gliese 832c is believed to be at least 5 times as massive as Earth. This added mass could mean a denser planet with stronger surface gravity, a thicker atmosphere, and a very different geological evolution. Whether those differences would hinder or enhance the development of life remains an open question, but the mere existence of such a world so nearby electrifies the scientific imagination. Early observations suggest the planet may possess a substantial atmosphere, though whether that atmosphere supports habitability or stifles it depends on a delicate balance of greenhouse effects, surface pressure, and chemical composition. A runaway greenhouse effect, like the one that transformed Venus into an infernal wasteland, remains a possibility. But so too does the dream that Gliese 832c could be wrapped in clouds and oceans, with a breathable sky and a surface temperate enough for life to emerge. The planet's close orbit to its host star means it may be tidally locked, forever showing one face to the star, while the opposite side remains in darkness. If so, the terminator line, the twilight region between the hot day side and cold night side, could offer a unique band where conditions are neither scorching nor frozen, but balanced in perpetual dusk. Here, in that narrow belt of eternal sunset, life could theoretically find a foothold. Gliese 832c stands as a reminder that while our own solar system is aging and transforming, the galaxy around us is dynamic, varied, and rich with unknowns. The planet's discovery in the early 21st century was made not through direct imaging, but by studying the subtle gravitational wobbles of its parent star, a technique known as radial velocity. These small shifts in starlight carry immense meaning. They speak of unseen worlds pulling gently at suns, of planetary systems unfolding in patterns invisible to the eye, but vivid through mathematics and spectrometry. Though no telescope has yet captured an image of Gliese 8032c, its presence is not theoretical. It is measurable, consistent, and gravitationally real. It offers a tantalizing destination for future missions, and its relative proximity means that one day robotic explorers, or perhaps even humans, might gaze up at a crimson sky from its surface. And in that moment, we may no longer ask if Earth is alone, but how many other Earths were simply waiting to be seen. As we consider Gliese 832c, a planet circling a modest star under a curtain of interstellar dust, we are drawn toward the grander pattern of cosmic collisions and structures that shape galaxies themselves. For just as Gliese 832c orbits within a peaceful zone, there are places where galaxies collide with such force that entire structures are reformed in luminous wheels. One such place exists farther out like a frozen ripple in the fabric of the cosmos, a place known as the Cartwheel Galaxy. Beyond the nearby hush of red dwarfs and the quiet potential of super-Earths like Gliese 832c, the universe shifts into grander scales. Here, silence becomes movement, and time bends to the will of forces far older and more violent than any planetary system. In these distant arenas, the cosmos sculpts its largest canvas. To understand the Cartwheel Galaxy, we must first remember that galaxies are not static islands. They move, drawn to one another by mutual gravity, influenced by the dark matter scaffolding that binds the cosmic web. The Cartwheel was once a typical spiral galaxy, not unlike our own Milky Way, but its fate was altered when a smaller galaxy plunged through its center. This event, lasting only a brief moment in cosmic terms, sent powerful shockwaves outward through the spiral's stars, gas, and dust. It was as if a stone had been thrown into a calm cosmic pond, and the resulting ripple, frozen by scale and distance, became the signature of the Cartwheel. The galaxy's appearance today is unlike any other. It features a bright, dense core, what remains of the original galactic nucleus, surrounded by a vast outer ring that glows with newborn stars. This ring is not a permanent feature, but the result of those shock waves. Density waves compressing clouds of gas as they move outward, triggering star formation in a brilliant, expanding circle. The ring now spans more than 150,000 light-years, and its perimeter is laced with clusters of hot, massive, short-lived stars. These stars live fast and die young, burning with blue intensity before ending in supernovae, further enriching the surrounding medium and adding new waves of heat, light, and chemical complexity. Between the core and the outer ring is a less luminous transitional zone, a region of chaos where older stars remain scattered, gravitationally disoriented by the collision, and where turbulent forces still ripple through the galactic disk. The symmetry of the ring might suggest serenity, but it masks a violent history of gravitational contortions, tidal forces, and matter swept out of order. And yet, from this disorder has come new creation. More than just a visual oddity, the cartwheel is a laboratory for understanding galactic evolution, showing how collisions do not always destroy, but often give rise to unexpected structures. Astronomers studying the cartwheel have used both optical and X-ray observations to map its structure and internal dynamics. The Chandra X-ray Observatory has revealed dozens of ultra-luminous X-ray sources scattered through the ring, likely black holes or neutron stars born from massive stellar deaths. Meanwhile, infrared telescopes peer through dust to trace the hidden nurseries where stars are still forming. Each wavelength paints a different layer of the galaxy's ongoing transformation, like a multi-tiered fossil record written in energy. One of the most astonishing aspects of the cartwheel is the sense of time it carries. What we observe today is not the moment of collision, but the reverberation of that event hundreds of millions of years later. The outer ring continues to expand outward, but not forever. Eventually, the wave will weaken, the ring will fade, and the cartwheel symmetry will dissolve back into irregularity. But for now, caught in this snapshot of dynamic balance, we witness a fleeting sculpture of order born from impact. In a universe where density and dissolution endlessly cycle, the cartwheel galaxy serves as a monumental expression of both. It embodies how even catastrophic collisions can lead to beauty and rebirth. Where Gliese 832c offered the hope of life in gentle orbits, the cartwheel reminds us that even violent interactions can carve new paths for stellar evolution, giving rise to entire generations of suns and worlds yet unseen. And as the ring continues to drift outward into the galactic dark, it echoes another movement, subtle and strange, in the icy frontier of our solar system. Far beyond Neptune, in the dim reaches where sunlight is no more than a whisper, orbits a distant, peculiar world with a tilted rotation. It does not shine like a galaxy or burn like a star, but it carries with it the memory of ancient collisions and the slow sculpting of the outer solar system. That world is called Gong Gong. In the far-flung corners of the cosmos, we find evidence of transformation on grand scales. Galaxies reshaped by impact, stars ignited by collision, yet closer to home. Within the fragile reaches of our own solar system, a different kind of transformation unfolds in quiet obscurity. It does not erupt in bursts of light or sweep across the sky in rings of fire. Instead, it turns slowly, tilted and distant, cloaked in cold shadow. This place is Gong Gong, a dwarf planet drifting in the outer solar system, a world both familiar and alien, shaped not by cosmic violence but by time, gravitational dance and silent persistence. Gong Gong resides far beyond the orbit of Neptune in a region known as the Scattered Disk, a realm populated by icy bodies left over from the earliest formation of the solar system. While Pluto and Eris are more well-known members of this distant family, Gong Gong has steadily earned its place among these ancient survivors, discovered in the early 21st century through painstaking sky surveys. It stands as one of the most massive known trans-Neptunian objects, rivaling the size and brightness of Pluto's fellow dwarfs, yet remaining shrouded in an atmosphere of mystery. What distinguishes Gong Gong is not merely its size or remoteness, but its unusual rotational tilt, a characteristic that offers rare insight into its history. Unlike most planets, which rotate along axes that are roughly perpendicular to the planes of their orbits, Gong-Gong's axis is wildly tilted, lying nearly sideways. Its poles sweep across the solar wind like giant cosmic paddles, exposing one hemisphere after another to long, drawn-out seasons that may last hundreds of Earth years. This extreme obliquity hints at a catastrophic past, a massive collision, perhaps with another distant body, that knocked it askew and set it spinning off axis. In this tilt lies a frozen memory, a gravitational scar still etched into the planet's behavior. Gong-Gong's surface is coated in ice, primarily water ice, with traces of methanol and perhaps other complex hydrocarbons. This chemistry gives it a reddish hue, distinguishing it from the bluer tints of some of its neighbors. The coloration suggests ongoing, slow processes of radiation-induced alteration, a kind of cosmic weathering caused by the constant bombardment of charged particles from the distant sun and cosmic rays from deeper space. In this sense, Gong-Gong is not merely a relic, but a participant in a continuing dialogue between solar energy and frozen matter. In 2020, he said, "In Plusavone, orbiting this enigmatic dwarf is a small moon named Xiang Liu, after a many-headed serpent from Chinese mythology, just as Gong-Gong itself is named for a destructive water deity. Their mythological names are fitting, for they seem to embody balance and chaos. The moon helps stabilize Gong-Gong's strange rotation to a degree, and may one day allow astronomers to calculate the dwarf planet's mass with far greater accuracy. With better data, we may uncover whether Gong-Gong hides a subsurface ocean, as some icy bodies do, warmed not by proximity to the sun, but by tidal interactions and internal decay. If so, even here, in this remote darkness, there may be a flicker of the conditions that once seeded life in the inner solar system. Gong-Gong's orbit is elongated and stretched, taking more than 6 centuries to complete a single journey around the Sun. It is a world that moves slowly, yet its very existence reshapes our understanding of planetary classification, dynamics, and the outer solar system's formation. Before the discovery of objects like Gong-Gong, Pluto was seen as an anomaly. Now, we understand that the solar system's outer shell is rich with bodies that challenge our definitions and deepen the mystery of what it means to be a planet. In studying Gong-Gong, we are not simply mapping ice and tilt. We are tracing the fingerprints of planetary migration, early solar turbulence, and gravitational resonance. We are reaching into the vault of time itself, trying to piece together a narrative told not in words, but in orbits and chemical residues. The same processes that scattered these icy objects to the solar frontier once shaped the architecture of every world, including our own. In Gong-Gong's tilted solitude, we find echoes of a younger solar system, still settling, still reshaping its margins. And as we shift from the icy corridors of our solar system toward more ancient stellar formations, our attention is drawn to the inner sphere of another kind of celestial architecture, densely packed, spherical clusters of some of the oldest stars in the galaxy. Suspended like glittering snow globes in the galactic halo, these clusters speak of primordial times. One of the most remarkable among them lies in the southern skies, blazing with aged light and gravity-bound density. It is called 47 Tucanae. In the outer solar system, Gong-Gong drifts alone, icy, tilted, and ancient, a solitary witness to the solar system's chaotic youth. But if we pull back even farther, Beyond the planetary orbits and out into the galactic halo, we find structures born not from fragmentation, but from tightly packed union. Here, drifting above and below the spiral disk of the Milky Way, are clusters of stars so old, so densely bound, that they predate much of what we understand as galactic structure. Among these relics of the early universe, one cluster stands out, not only for its richness in stars, but for the secrets it holds about time, gravity, and stellar evolution. This is 47 Tucanae. Tucked into the southern constellation Tucana, 47 Tucanae is a globular cluster, one of over 100 orbiting the Milky Way, like ancient sentinels, yet this one demands particular attention. From Earth, it appears as a bright, densely luminous smudge, just below the small Magellanic Cloud, though that neighboring dwarf galaxy is far more distant, at roughly 16,000 light-years away. 47 Tucanae is still part of our galactic halo, but it exists as a time capsule from an era before the Milky Way had fully assembled itself. The stars in 47 Tucanae are astonishing not only for their sheer number, several 100,000 packed into a relatively compact sphere, but also for their age. Most are more than 11 billion years old, formed at a time when heavy elements were scarce and the universe itself was still in its cosmic adolescence. These stars shine with a dim, reddish hue, having burned through their hydrogen long ago, many now residing in later stages of stellar evolution. The cluster's color magnitude diagram, a kind of stellar population map, reveals not the diversity of a galaxy, but the tight, disciplined story of a single burst of formation from the early cosmos. In such a crowded environment, the average distance between stars can be less than a light year, far closer than in our solar neighborhood, where stars are separated by many light years of empty space. This density creates extraordinary gravitational interactions. Stars within 47 Tucanae move like dancers in a packed ballroom, tracing complex, overlapping paths. Some even exchange partners in close stellar encounters. These interactions help explain the presence of exotic objects like blue stragglers, stars that appear younger and hotter than they should be. These may have formed through collisions or mergers, reigniting old stellar cores and confusing our sense of chronology. 47 Tucanae is also a fertile ground for studying pulsars, rapidly spinning neutron stars left behind by supernovae. The cluster contains more than 24 known millisecond pulsars, some locked in binary systems with white dwarfs. These stellar remnants act as cosmic clocks, pulsing with extraordinary regularity, and offering astronomers a tool to measure gravitational effects, test general relativity, and even search for the elusive gravitational waves that ripple through space-time. What makes globular clusters like 47 Tucanae even more intriguing is their origin. These clusters are not simply byproducts of the Milky Way. They may have come from outside it. Some theories suggest that many globulars are the cores of smaller galaxies cannibalized by the Milky Way during its growth. If true, then 47 Tucanae is not just a collection of stars. It is a fossil of galactic conquest, a memory of mergers preserved in stellar light. In observing 47 Tucanae, we are not merely looking at a cluster, we are peering into the early structure of the universe. Long before Earth, the Sun, or even the spiral arms of the Milky Way took shape. It is a monument to gravitational stability, a celestial hive that has endured for most of cosmic history. The stars within it may never host complex planetary systems. Conditions are too dense, encounters too frequent, but what they offer instead is even more rare. A glimpse into the physics of ancient starlight, unaltered by time. still whispering the conditions of the young cosmos. And as we trace the edge of the Milky Way's halo, descending once more toward the outer reaches of our planetary system, the landscape becomes stranger still. From the tightly bound to the faintly seen, we move from the luminous past to a world so subtle that even our best telescopes strain to catch its motion. It is vast, elusive, and barely visible. A moon that streaks through the shadows of Europe. Its name is Bianca. From the tightly wound core of 47 Tucana, a relic of the universe's earliest starlight, we travel again. Away from dense clusters and ancient suns, back through the fragile lanes of planetary systems, and into the boundless domain of possibility. Here, imagination and reality begin to converge, and what was once fantasy, once confined to the shifting sands of a cinematic desert, now rises in astronomical observation as fact. We enter the realm of Tatooine worlds, planets that orbit not one, but two suns. The idea of twin-star planets once lived only in fiction. When George Lucas introduced the twin sunsets of Tatooine in the late 20th century, they were a poetic image, a metaphor for longing, wonder, and alien beauty. But as astronomical tools sharpened and our eyes turned outward with greater precision, nature revealed that such worlds are not only possible, they are real, numerous, and in some cases, surprisingly stable. Known scientifically as circumbinary planets, these celestial bodies orbit around two stars that are themselves gravitationally bound to each other. These stars may be nearly identical in mass or dramatically different, burning at varied temperatures and brightness. As they dance around a common center of mass, the planet traces a path that loops around them both, not in chaos, but in a complex harmony dictated by the mechanics of gravity and orbital resonance. One of the first confirmed Tatooine worlds, Kepler 16b, proved once and for all that twin-star planets were not fiction. Located roughly 200 light-years from Earth, Kepler 16b is a gas giant roughly the size of Saturn, orbiting a binary system composed of a smaller red dwarf and a larger orange star. Despite its exotic position, the planet's orbit is surprisingly stable, completing a full journey around both suns every 229 days, and it is not alone. Since that discovery, astronomers have identified multiple circumbinary planets, Kepler 34b, Kepler 35b, and others, all offering variations of the same breathtaking truth, that planetary systems form and thrive in environments we once thought too volatile. In such systems, day and night cycles become complex. A sunrise might begin with one star cresting the horizon, followed moments later by its companion. Shadows dance in odd directions, the color of sunlight shifts with the angle of dual illumination, and seasons can behave in strange, elongated rhythms, depending on the orbital configuration. For any hypothetical life that might arise on such a world, adaptation would be shaped not only by planetary conditions, but by the gravitational ballet of its skies. The formation of circumbinary planets challenges traditional models of planetary accretion. Initially, it was believed that the gravitational turbulence between two stars would disrupt the protoplanetary disk, preventing planets from coalescing. Yet observations suggest otherwise. Over time, material beyond a certain critical radius, far enough from the binary to remain stable, can clump, cool, and give rise to fully formed planets. Some may migrate inward later, their orbits reshaped by the star's shifting gravities and mutual tugs. Others may be ejected into interstellar space altogether, becoming rogue planets. worlds without suns, wandering the void alone. What remains remarkable about Tatooine worlds is not only their existence, but their resilience. Their ability to maintain orbital coherence in dynamic systems hints at a deeper order within chaos, a hidden symmetry inside the swirling mechanics of gravity and time. And for astronomers, they are more than exotic headlines. They are laboratories for understanding how planetary systems form under non-standard conditions, how radiation varies in multistellar environments, and whether the boundaries of the habitable zone, where liquid water can exist, must be redrawn entirely when more than one sun is involved. Could life exist on a Tatooine-like world? That question now extends beyond speculation. If the right conditions align, if the planet maintains a stable temperature, holds an atmosphere and rotates to distribute heat, it is not unthinkable that life might arise. Dual star systems could offer dynamic climates, rich chemical cycles, and prolonged periods of light that drive photosynthetic processes in unfamiliar ways. The possibilities are vast, and our tools for searching them, transit detection, radial velocity measurements, and direct imaging, are becoming ever more refined. These are no longer fictional worlds. They're celestial facts, locked in orbits of elegance around luminous pairs. And their discovery reshapes what we understand about planetary diversity, challenging our assumptions and widening the scope of what is possible in the architecture of the cosmos. From these twin-lit landscapes, we turn now to another unique structure in space, one not made of stars or planets, but of raw interstellar material where gas and dust are ignited by radiation, sculpting forms that flicker like flame against the void. This place, burning softly in starlight, is called the Flaming Star Nebula. As Tatooine-like planets glide beneath twin suns in orbits born of harmony and turbulence, their complex rhythms draw us deeper into the possibilities of celestial mechanics. But while these circumbinary giants bask in luminous excess, there exist other worlds, smaller, fainter, and far more elusive, that slip quietly through the shadows of our own solar system. They do not blaze with fire or boast the grandeur of ringed giants. Instead, they whisper through the darkness, in low orbits, dimly lit and rapidly moving. One such world is Bianca, a tiny moon circling the distant ice giant Uranus. It is easy to overlook, but within its faint path lies a story of motion, proximity, and planetary complexity. Discovered in the late 20th century by the Voyager 2 spacecraft during its historic flyby of Uranus, Bianca was found not through brightness, but through precision. It is one of the inner moons of Uranus, a member of a compact, tightly packed family of satellites that orbit astonishingly close to their host planet. These moons form a kind of miniature system within a system. Small, irregularly shaped bodies that weave intricate paths just above Uranus's equator, locked into the planet's gravity and shadow. Bianca itself is no more than a speck in the astronomical sense. Roughly 30 miles across, it lacks the mass to shape itself into a sphere, instead resembling a lumpy potato-like shard of rock and ice. It is composed of the basic materials common to Uranian moons, water ice laced with dark carbonaceous compounds, its surface likely battered by micrometeoroid impacts that have left it darkened and pitted over eons. Unlike the distant dwarf planets or the majestic moons of Jupiter and Saturn, Bianca has no geological drama, no geysers, no subsurface oceans, no towering cliffs. But what it does possess is speed. Orbiting Uranus in just over 13 hours, Bianca races along a path that hugs the planet at a distance of only about 30,000 miles from its cloud tops. In this tightly bound orbit, it completes nearly 2 revolutions in a single Earth day. This proximity means that Bianca experiences powerful tidal forces, caught in the gravitational grip of a planet over 14 times the mass of Earth. These forces likely shape the orbits of the inner Uranian moons, keeping them confined to narrow lanes, while also slowly altering their positions over geological time. The system Bianca inhabits is more than a collection of small rocks. It is a dynamic ring and moon complex, where each moon interacts gravitationally with its neighbors and with the faint rings of Uranus. These interactions are subtle but persistent, tiny orbital adjustments, slow migrations, and periodic nudges that can destabilize moons over long periods. The Uranian inner moon system, including Bianca, may be in a delicate state of balance, susceptible to shifts that could one day lead to collisions or reconfigurations. Models suggest that some of these moons, including Bianca, may eventually be torn apart by tidal stresses or fall inward, becoming part of the very ring structures they now skirt. Bianca's place within this dance is a reminder that even the smallest celestial bodies have stories, shaped by gravity, inertia, and time. Though we see only hints of its surface and trace only its rapid orbit, Bianca is part of a living system, one that evolves on slow, invisible timescales. It challenges us to appreciate the complexity hidden within the understated, to recognize that significance is not always measured by size or brilliance. Studying moons like Bianca sharpens our understanding of planetary formation and orbital dynamics. It helps refine models of how moons migrate, how rings form, and how systems maintain equilibrium, or fall out of it. And as our telescopes improve and our missions reach farther, we may yet uncover more details about this hidden corner of the Uranian system, where silence reigns, but motion never ceases. From the quiet race of Bianca around its icy host, we now leap across vast scales again, not to a moon or a planet, but to one of the largest known structures in the observable universe. In the distant cosmic dark, galaxies thread together in chains stretching for hundreds of millions of light-years. One such structure, monumental in size and staggering in complexity, is called RxJ 1000, 347.5 11.45, from the rapid shadow-bound orbit of Bianca, a moon flickering close to Uranus like a faint ember caught in a giant's breath. We now ascend into an entirely different dimension of scale. Beyond planetary systems, and even beyond single galaxies, the universe begins to take shape in colossal, interlinked structures formed not by solitary bodies, but by gravitational congregation on the grandest level. These are galaxy clusters, enormous gatherings of galaxies bound together by gravity, surrounded by halos of dark matter and veiled in clouds of superheated gas. Among these immense titans, few are as massive, as luminous, or as violent in energy output as RxJ 1000, 347.511.45. Situated over 5 billion light-years from Earth in the direction of the constellation Centaurus, RxJ 1000, 347.511.45, is not merely a collection of galaxies. It is an extreme expression of gravitational assembly. This galaxy cluster is one of the most massive ever discovered. It is a cathedral of structure, forged over cosmic time by the relentless pull of matter gathering more matter. a monument to the scale of what gravity can build when left unchecked across billions of years. At the heart of RxJ 1000, 347.5 1145 lie hundreds of galaxies, ranging from massive elliptical giants to smaller star-forming spirals. Each galaxy, in turn, contains hundreds of billions of stars and potentially countless planets orbiting them. But the galaxies themselves comprise only a fraction of the cluster's total mass. Far more lies unseen in a ghostly shroud of dark matter, whose gravitational influence binds the cluster together, shaping the motion of galaxies and the very architecture of space-time within it. And between these galaxies, filling the space like an invisible ocean, is an immense quantity of hot, ionized gas known as the intra-cluster medium. This gas, heated to tens of millions of degrees, glows not in visible light but in X-rays. It was through this glow that RxJ 1000, 347.5 1145, was first revealed to us. Its name drawn from its X-ray signature catalogued by the Rosat satellite in the early 1990 era. Subsequent observations, particularly by the Chandra X-ray Observatory and the Atacama Large Millimeter/Submillimeter Array, ALMA, uncovered an environment of staggering temperature, mass and energy. The intense heat observed in this cluster is not uniformly distributed. One quadrant of RxJ 1000, 347.5 1145, burns significantly hotter than the rest, suggesting that we are witnessing the aftermath of a colossal collision. A smaller cluster or group of galaxies likely slammed into the larger system at high speed, compressing and heating the gas through shock waves. This event has not only created vast streams of turbulent gas, but also generated pressure so immense that it has become one of the strongest examples of the Salyut-Zidovich effect ever measured. In this phenomenon, photons from the cosmic microwave background, relic radiation from the Big Bang, gain energy as they pass through the hot plasma of the cluster, providing a new way to map mass and temperature in distant cosmic structures. In studying this massive cluster, scientists are able to test theories of cosmic evolution, galaxy formation, and the large-scale structure of the universe. RxJ 1000, 347.5 1145 becomes not merely an object of observation, but a tool, an anchor point in the scaffolding of the cosmos. It demonstrates how galaxies are not scattered randomly, but arranged in filaments, walls, and nodes that form the cosmic web. This cluster sits like a jewel at one of those intersections where matter converges, energy roils, and time is written in collisions. And yet, even in such vastness, the narrative of the universe continues to unfold on smaller, more delicate scales. Just as gravity binds galaxies into clusters, it also allows tiny worlds to form around distant stars, some so subtle, so recently detected that they have only begun to enter our charts. From this galactic storm, our focus returns now to a quiet system orbiting a small red dwarf. There, a rocky world named K23d circles its star with calm precision, inviting questions not about mass or heat, but about the potential for life. In the vast cosmic arenas like RxJ 1000, 347.5 1145, where galaxies swarm through oceans of hot gas and space is twisted by gravity itself, we witness the universe in its grandest expressions. Yet, even amid that towering scale, there lies another, form of wonder. Quiet, intimate, and closer to the scale of life as we know it. For while galaxy clusters show us the skeleton of the cosmos, it is within the modest orbits around single stars that we began to ask different questions about warmth, atmosphere, and the conditions that might nurture life. One such world, fragile in size but potent in implication, is K23d, a small rocky planet orbiting a red dwarf star not far from our own galactic neighborhood. K23d belongs to a planetary system discovered by NASA's K2 mission, the successor to the original Kepler Space Telescope, which was designed to search for Earth-sized planets orbiting distant stars. The planet was detected using the transit method, an approach that observes the faint dimming of starlight as a planet crosses in front of its host star. This subtle dip, lasting only hours, is enough to reveal not only the existence of a planet, but also clues about its size, orbit, and potential composition. Orbiting a cool MTH red dwarf known as K23, the planet K23d resides within the star's habitable zone, the delicate band of distance where temperatures might allow liquid water to exist on the planet's surface. This does not confirm habitability, of course, but it does raise the possibility. Red dwarfs are smaller and cooler than the Sun, meaning that their habitable zones lie much closer to the star. K23d completes a full orbit in just under a month, tightly hugging its stellar host in a path that might, under the right circumstances, offer a stable and temperate climate. The star itself is dimmer than our Sun by orders of magnitude. From the surface of K23d, if it possesses a surface, the sky would likely glow in hues of orange and crimson, its sunlight filtered through a different spectrum. Depending on atmospheric thickness and composition, the planet could maintain warmth through greenhouse effects, potentially supporting environments where water remains in liquid form. But red dwarfs present unique challenges. They are known for stellar flares, magnetic storms that can bombard orbiting planets with bursts of radiation. For life to survive or even arise under such conditions, a planet would likely need a protective atmosphere or magnetic field, features that are still unconfirmed for K23d. Unlike the massive exoplanets that dominate early discovery catalogues, gas giants and hot Jupiters, K23d is small and likely rocky, possibly similar in mass and composition to Earth. This similarity makes it an important target for further observation, particularly for missions capable of characterizing atmospheres. With tools like the James Webb Space Telescope and next-generation ground-based observatories, scientists hope to one day examine the spectral fingerprint of this planet's atmosphere, searching for water vapor, carbon dioxide, methane, or even molecular oxygen, each a potential clue in the search for biological processes. Beyond its physical characteristics, K23d symbolizes a new frontier in exoplanetary science. It is part of a growing list of temperate exoplanets orbiting nearby stars, forming the basis for future exploration, perhaps even interstellar visitation in the distant future. Though small and dim from Earth's perspective, it holds immense significance for the question that quietly underlies so much of astronomy. Are we alone? Red dwarf stars like K23 are among the most common in the galaxy. They outnumber Sun-like stars by far and often host small rocky planets. This statistical reality suggests that the number of potentially habitable planets may be far greater than once imagined, not just dozens, but perhaps millions across the Milky Way. Each one is a laboratory of chemistry, pressure, temperature, and time. Each is a story, unfolding beneath alien skies. whether barren or brimming with life, yet unknown. In the story of K23d, we see the bridge between detection and understanding, between the shadow of a distant transit and the glimmer of possibility. It stands as a symbol of the precision and hope that modern astronomy can offer, urging us to keep looking, to keep asking. And so, from this calm, Earth-sized world, bathed in the red glow of a quiet star, we turn our attention once more to raw elemental force, to a place where light and matter combust in a radiant storm. There, among clouds of dust and glowing gas, is a stellar nursery born of fire and starlight. This is the flaming star Nebula. From the calm, red-lit orbits of exoplanets like K23d, where the potential for habitability stirs beneath a modest glow, we now return to the raw, unformed edge of stellar evolution, to places where stars are not yet settled, but are still becoming. These are not systems in quiet balance. They are regions alive with motion, color, and violence. Here, gravity, radiation, and time converge to ignite the interstellar medium, sculpting fire from darkness. In one such region, luminous and turbulent, gas and dust catch fire in starlight. This is the flaming star Nebula. Located in the northern constellation Auriga, the flaming star Nebula, officially known as IC 405, is a striking blend of reflection and emission nebulae. Spanning over 5 light-years across, it represents one of the many dynamic cloudscapes in which new stars are formed and old starlight still lingers. What gives this nebula its unique appearance is its relationship with a hot, lying star embedded within it, AE Aurigae. This star is not a native of this region, but rather a stellar vagabond, hurled from its birthplace by gravitational chaos, likely involving a multi-star interaction or a long-past supernova. Now speeding through the nebula at high velocity, it ignites the gas and dust in its path like a cosmic blowtorch. The nebula itself is composed largely of hydrogen gas, the most basic and abundant element in the universe, along with trace amounts of oxygen, nitrogen, and carbon-based dust grains. As AE Aurigae moves through this medium, its intense ultraviolet radiation ionizes the surrounding hydrogen atoms, stripping away electrons and creating a soft, red glow characteristic of emission nebulae. This ionized light is the nebula's heartbeat, evidence of energetic transformation on an interstellar scale. Simultaneously, starlight also reflects off the fine dust in the cloud, scattering into a bluish hue. The combination creates a surreal palette of deep crimsons and smoky blues, as if the region itself is caught between combustion and reflection. La Sissi au clair. But the flaming star nebula is not merely a visual spectacle. It is an evolving system, shaped by wind, radiation pressure, and the slow gravitational collapse of molecular clouds. The radiation from AE Aurigae carves out cavities and channels in the gas, shaping filaments and arcs through which particles flow. These structures are not decorative. They are functional, tracing the directions of magnetic fields, mapping shock fronts, and delineating regions where star formation is still quietly underway. Within the cooler, denser pockets of the nebula, gravity continues its patient work, pulling gas together into knots that may one day ignite into new stars of their own. Astronomically speaking, AE Aurigae is an Otal star, one of the hottest and most luminous spectral classes. Stars like this burn quickly and die young, often ending in dramatic supernovae. Their lives, though brief, are intensely influential, injecting energy, radiation, and heavy elements into their surroundings. In a galaxy like the Milky Way, where star formation pulses in waves, the flaming star nebula is one of many cradles for new generations of stars, but few are as vividly illuminated by such a bright, solitary traveler. To study the flaming star nebula is to glimpse a moment in stellar migration and cosmic sculpting. It shows how stars interact with their environments, not passively, but through radiation and force. It reveals how nebulae are not just backdrops to starlight, but actors in the drama of creation, and how the balance of light, matter, and motion brings complexity from the simplest building blocks of hydrogen and dust. And just as this nebula is shaped by a star in motion, driven forward through a cloud, so too do planets sometimes share such orbital fates, born into dynamic, sometimes catastrophic systems. Among the most intriguing of these are the hot, chaotic environments where massive planets spiral toward their stars in doomed trajectories. The eighth destination, Noma. One such world may exist in the WASP-12 system, a planetary sibling cast into a race against time. In the flaming star nebula, light sculpts gas into form and motion into brilliance, a vivid reminder that the universe is not static, but in constant transformation. Stellar winds carve through molecular clouds, triggering birth even as they hasten decay. But not all cosmic transformations lead to creation. Some mark decline, spirals inward, and ultimate collapse. From the glowing womb of stars, we shift our gaze to a different kind of evolution, one marked by doom, decay, and the slow destruction of a planetary system. Here, around a star known as WASP-12, we encounter a planetary world that may not endure, and beside it a possible sibling, WASP-12c, moving through a gravitational ballet whose outcome may already be sealed. The WASP-12 system lies roughly 1,400 light-years from Earth in the constellation Auriga. It gained scientific attention with the discovery of WASP-12b, an ultra-hot, Jupiter-sized planet, so close to its parent star that its atmosphere is being stretched, stripped, and consumed. This intense interaction, a planetary death spiral, has made the system a subject of extensive study. But within this maelstrom, there may be another presence, a planet not yet fully confirmed, known as WASP-12c. It orbits farther out, potentially providing a rare chance to study not just a dying planet, but a complex, multi-planet system on the edge of stability. What draws astronomers to WASP-12c is not merely its proximity to a doomed sibling, but what it reveals about gravitational dynamics in systems under extreme stress. In tightly packed planetary arrangements, gravitational resonances can develop, relationships where the timing of each planet's orbit influences the others in predictable but potentially unstable ways. WASP-12c, if it exists, likely plays a role in modulating the orbit of WASP-12b. This modulation could be driving WASP-12b even closer to its star, speeding up its destruction. In this way, the two planets may be locked in a kind of slow, spiraling fatalism, their fates intertwined by invisible lines of force. The system's host star, WASP-12, is a yellow-white dwarf, somewhat more massive and hotter than our Sun. Over time, its radiation has inflated WASP-12b's atmosphere, creating a bloated, comet-like tail of gas escaping into space. The rate of this mass loss is staggering. Astronomers estimate that millions of tons of planetary material are being stripped away each second. This material doesn't vanish. It forms a torus of gas around the star and may even fall inward, creating a faint accretion signature. WASP-12 is not just shining, it is feeding, consuming the very planet it gave light to. And if WASP-12c is confirmed, it may be the silent witness to this destruction, or perhaps even its subtle cause. The implications extend far beyond this single system. For much of astronomical history, planetary systems were assumed to mirror our own, stable, circular, clockwork in their regularity. But WASP-12 defies that model. Its inner planet's highly eccentric, decaying orbit suggests that many systems may be chaotic, shaped by early violence or long-term instability. Perhaps WASP-12b formed farther out and migrated inward, driven by gravitational pushes from WASP-12c, or even an earlier third planet that has since been ejected or destroyed. What we observe now may be the final act of a long, invisible drama, a system tearing itself apart under the weight of its own history. WASP-12c remains unconfirmed, partly because detecting planets in complex systems like this one requires long-term monitoring and extremely precise measurements. Transit timing variations, subtle changes in when WASP-12b passes in front of its star, suggest the gravitational influence of another object. Radial velocity studies, which detect the wobble of the star under planetary tugs, also hint at its presence, but until more data accumulate, WASP-12c exists in the liminal space between prediction and discovery, a ghost planet on the threshold of confirmation, orbiting a star where everything is in motion and nothing is permanent. And while some systems fall inward toward heat and disintegration, others are torn outward, flung from their origins into the intergalactic dark. Some galaxies, like WASP-12b, cannot hold on to all they once embraced. One such system is ESO 137-1, a galaxy caught mid-flight, trailing a stream of stars like glowing debris from a forgotten collision. This dying system invites deep reflection. What happens to planets as stars age or environments shift? How many worlds have come and gone before we learn to look beyond our own skies? WASP-12c remains unconfirmed, partly because detecting planets in complex systems like this one requires long-term monitoring and extremely precise measurements. Transit timing variations, subtle changes in when WASP-12b passes in front of its star, suggest the gravitational influence of another object. Radio velocity studies, which detect the wobble of the star under planetary tugs, also hint at its presence. But until more data accumulate, WASP-12c exists in the liminal space between prediction and discovery. A ghost planet on the threshold of confirmation, orbiting a star where everything is in motion and nothing is permanent. Yet, whether confirmed or not, WASP-12c's possible existence reminds us that planetary systems are not static arrangements. They are dynamic, evolving, and sometimes self-destructive. They respond to the unseen forces of migration, resonance, and stellar feedback. In WASP-12, we see a kind of cosmic entropy, a planetary candle burning too close to its flame, watched, perhaps, by a companion tethered to the same fate. In the vast, ever-expanding frontier of human exploration, there exists a journey so awe-inspiring and monumental that it transcends the very boundaries of time and space. This epic voyage is none other than the extraordinary odyssey of Voyager 1, a pioneering spacecraft launched by NASA that has traveled farther than any other human-made object, carrying the hopes and dreams of humanity into the deepest reaches of the cosmos. Recently, Voyager 1 sent back a historic transmission to Earth that has ignited waves of excitement and curiosity throughout the global scientific community and beyond. At the heart of this remarkable message lies a discovery of unparalleled significance, an enigmatic object detected in the profound, uncharted depths of interstellar space. This mysterious revelation has reignited one of the most timeless and compelling questions that has captivated humanity for generations. Could this signal represent the long-awaited moment when we finally establish contact with advanced extraterrestrial life? For centuries, humankind has gazed up at the night sky with wonder, imagining the possibility of other civilizations thriving among the stars. Now, this revelation has brought those age-old dreams tantalizingly close to reality. Voyager 1's journey began decades ago when it was launched on September 5, 1977, as part of NASA's ambitious Voyager program. Its mission was bold and profound: to act as Earth's emissary, venturing beyond the familiar realms of our solar system into the vast unknown. While meticulously studying the outer planets and their moons, Voyager 1's remarkable voyage was marked by a serendipitous cosmic alignment. It set off just 16 days before its twin, Voyager 2, beginning a cosmic ballet that has unfolded for more than 40 years. What truly sets Voyager 1 apart from countless other space missions is its extraordinary spirit of communication. Despite its unfathomable distance from Earth, Voyager 1 maintains a steadfast dialogue with our home planet through NASA's venerable deep space network. This complex and powerful communication system allows Voyager 1 not only to receive commands, but also to transmit back invaluable streams of scientific data, bringing us ever closer to understanding the cosmos. As of the latest measurements, Voyager 1 is an astonishing 159.32 astronomical units AU away from Earth, equivalent to nearly 23.8 billion kilometers, or approximately 14.8 billion miles. This staggering distance makes it the most distant human-made object ever to voyage into space. Yet, despite this incredible remoteness, Voyager 1's instruments continue to operate, tirelessly collecting and sending back information that deepens our understanding of the universe around us. Voyager 1's primary mission was to explore the outer boundaries of the heliosphere, the vast bubble of charged particles and magnetic fields generated by the Sun. This outer boundary, called the heliopause, marks the frontier where the influence of our star gives way to the cosmic environment of interstellar space. Crossing this threshold in 2012, Voyager 1 became the first human-made object to enter the space between stars, beginning a new chapter in space exploration. What makes Voyager 1's mission truly remarkable is not only its groundbreaking discoveries, but also its extraordinary endurance. Originally designed to last only a few years, Voyager 1 has surpassed all expectations, continuing its interstellar journey for over 4 decades. Each day, it cruises through the void at an incredible speed of approximately 38,000 miles per hour, sending precious data back to Earth across billions of miles. Scientists anticipate that Voyager 1 will continue this historic mission at least until 2025, when its power sources are expected to diminish. Equipped with a sophisticated suite of 10 scientific instruments, including cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray sensors, and radio science equipment, Voyager 1 was built to be humanity's eyes and ears in the cosmos. These instruments have enabled the spacecraft to withstand the harsh and unforgiving conditions of deep space, while delivering an unprecedented wealth of knowledge about the outer solar system and beyond. Among Voyager 1's most celebrated achievements are its close flybys of two colossal gas giants, Jupiter and Saturn. In 1979, Voyager 1 made its first close approach to Jupiter, revealing breathtaking details about the planet's turbulent atmosphere, intricate ring system, and diverse moons. The spacecraft's instruments confirmed the existence of faint rings around Jupiter, previously only theorized, and uncovered previously unknown moons that added to our understanding of the planet's complex environment. A year later, in 1980, Voyager 1's encounter with Saturn provided equally stunning insights. It unveiled the intricate structure of Saturn's iconic rings, captured detailed images of its moons, and deepened our knowledge of the planet's magnetic field and atmosphere. These flybys not only revolutionized planetary science, but also inspired a new generation of explorers, scientists, and dreamers around the world. One of the most iconic moments in Voyager 1's journey came in 1990, when the spacecraft, prompted by the visionary astronomer Carl Sagan, turned its cameras back toward Earth and captured the now famous image known as the pale blue dot. In this extraordinary photograph, Earth appears as a tiny speck suspended in a vast cosmic ocean, a fragile and precious home floating in the immense void of space. This image remains a powerful symbol of humanity's shared vulnerability and interconnectedness, reminding us of the urgent need to cherish and protect our only home. As Voyager 1 continues its silent journey through the darkness beyond our solar system, it carries with it the legacy of human curiosity, ingenuity, and the unquenchable desire to explore. Its latest discovery in the depths of interstellar space hints at new cosmic mysteries waiting to be unveiled, perhaps even the momentous encounter with other life forms that so many have dreamed about. This odyssey, which began over 4 decades ago, continues to inspire and challenge us, inviting us all to look up, wonder, and reach ever further into the vast expanse of the universe. Voyager 1 was designed to push the boundaries of human knowledge, traversing vast distances where no spacecraft had dared to go before. Equipped with a suite of sophisticated scientific instruments, it was tasked with studying the giant planets and their moons, capturing unprecedented data that would forever change our understanding of the solar system. What makes Voyager 1 truly extraordinary is not just its groundbreaking discoveries, but its resilience and longevity. Despite being launched over 4 decades ago, it continues to send invaluable information back to Earth, maintaining a lifeline of communication through NASA's Deep Space Network. This unwavering connection allows scientists to receive data from more than 14 billion miles away, a testament to human ingenuity and determination. As Voyager 1 journeys beyond the heliosphere, the protective bubble created by the Sun's solar wind, it enters interstellar space, a vast expanse filled with cosmic mysteries. Recently, a signal from Voyager 1 revealed the detection of an enigmatic object lurking in this farthest frontier. This revelation has sent shockwaves through the scientific community and reignited a question that has fascinated humanity for generations. Are we alone in the universe? The possibility that this mysterious detection could be evidence of advanced, extraterrestrial life has captivated imaginations worldwide, inspiring scientists, philosophers, and dreamers alike to ponder the cosmic significance of this discovery. As we delve deeper into Voyager 1's findings, we are reminded of the boundless curiosity that drives human exploration, our relentless quest to understand not only the universe, but our place within it. In this unfolding cosmic saga, Voyager 1 stands as a symbol of hope, perseverance, and the unquenchable thirst for knowledge. Its voyage is not merely a scientific endeavor, but a profound journey that connects us all, uniting humanity in awe of the infinite cosmos that stretches beyond our wildest dreams. An intriguing aspect of the Voyager mission narrative lies in the remarkable timing. Voyager 1 began its epic journey just 16 days ahead of its cosmic twin, Voyager 2. This serendipitous alignment lends a sense of cosmic symmetry to an unparalleled saga. Two intrepid emissaries of humanity, launched in close succession, each destined to explore the uncharted realms of our solar system and beyond. What truly distinguishes Voyager 1 from countless other space missions is its indomitable spirit of communication, a lifeline that it maintains steadfastly with Earth across unimaginable distances. This extraordinary feat is made possible by NASA's venerable Deep Space Network, a robust and sophisticated communication infrastructure designed to ensure a constant dialogue between the spacecraft and its home planet. This unyielding link serves a dual purpose. It allows Voyager 1 to receive precise commands from mission control and, in return, to transmit a treasure trove of invaluable scientific data back to its terrestrial origins. According to the most recent data, Voyager 1 currently finds itself at an astonishing distance of approximately 159.32 astronomical units (AU) from Earth. To put this monumental achievement into perspective, this distance translates to an awe-inspiring 23.834 billion kilometers, or roughly 14.8 billion miles, away from the cradle of humanity. In other words, Voyager 1 is now the most distant human-made object in existence, a lone traveler venturing farther into the cosmic ocean than any other craft before it. This staggering remoteness not only speaks to the spacecraft's incredible durability and the brilliance of human engineering, but also marks a milestone in our quest to understand the universe around us. It is this incomprehensible remoteness that firmly establishes Voyager 1 as the most distant human-made object ever to embark on an odyssey into the vast cosmos. From the moment of its launch, Voyager 1's primary mission objective was clear and profoundly ambitious: to explore and meticulously scrutinize the boundaries of the outer heliosphere, a mysterious and barely understood region known as the heliopause. This invisible boundary marks the outermost layer of the Sun's influence, the final frontier where the solar wind meets the vast interstellar medium, enveloping our entire solar system in a protective bubble. Through its relentless investigations, Voyager 1 has bestowed humanity with invaluable insights into the cosmos, especially within the confines of our immediate solar neighborhood. Propelled forward at an astonishing velocity of approximately 38,000 miles per hour, an incredible speed that allows it to traverse vast cosmic expanses day by day, the spacecraft continues to push the boundaries of exploration and knowledge. Yet, what truly sets Voyager 1 apart is not just its distance or speed, but its remarkable endurance. The spacecraft has not merely met expectations, it has far exceeded its originally projected lifespan. More than 4 decades after its historic launch, Voyager 1 remains operational, tirelessly sending back vital data from the farthest reaches of space. Its ongoing mission serves as a testament to human ingenuity, perseverance, and an insatiable desire to understand the universe around us. Voyager 1 has embarked on extraordinary decades of exploration, defying the limits of time and technology. Each passing day, this remarkable spacecraft dutifully records and transmits vital information about its celestial journey, offering humanity a continuous stream of priceless data from the edge of our solar system and beyond. Remarkably, Voyager 1 is expected to continue this awe-inspiring interstellar sojourn until at least the year 2025, a testament to its resilient propulsion systems and enduring power supply that have kept it operational far beyond initial expectations. By that time, it is estimated that Voyager 1 will have achieved an almost inconceivable distance of approximately 13.8 billion miles from the nurturing embrace of the Sun, a staggering measure of its pioneering voyage into the cosmic unknown. Accompanying Voyager 1 on this grand adventure is its celestial sibling, Voyager 2, both launched as part of NASA's legendary Voyager program. Together, they were equipped with a formidable array of 10 unique scientific instruments, each serving as sensory extensions of the spacecraft into the vast cosmos. This sophisticated ensemble of tools included television cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray and charged particle sensors, as well as state-of-the-art radio equipment, all meticulously designed to conduct groundbreaking experiments. These ingenious instruments have endowed Voyager 1 with the resilience and capability to withstand the harsh and unforgiving environs of deep space, allowing it to probe the unfathomable reaches of the unknown. One of the most indelible milestones in Voyager 1's storied journey was its close encounters with two of the most majestic and enigmatic bodies in our solar system, Jupiter and Saturn. These historic flybys provided humanity with an unprecedented window into the complexities and wonders of these gas giants, forever reshaping our understanding of the planetary giants and their moons. Voyager 1's encounters with the solar system's colossal planets, Jupiter and Saturn, were nothing short of historic. These celestial rendezvous, which occurred in 1979 and 1980, respectively, marked a watershed moment in the annals of scientific discovery. Through these close flybys, Voyager 1 gifted humanity with an unprecedented glimpse into the intricate complexities of these gas giants and their enigmatic retinues of moons. The spacecraft etched its name indelibly into history by uncovering previously unknown moons orbiting these planets, and by revealing the intricate and delicate ring structures that encircled both Jupiter and Saturn. Prior to Voyager 1's mission, much of this was speculation or incomplete knowledge. Its groundbreaking revelations not only captivated the scientific community, but also ignited the imaginations of people across the globe, heralding a new era of planetary exploration. One of Voyager 1's most iconic and enduring contributions to our cosmic understanding came in 1990 when the celebrated astronomer Carl Sagan championed a visionary concept. He urged the spacecraft to pivot its cameras and direct its lens back towards Earth. This simple yet profound act resulted in the creation of the now famous image known as the pale blue dot. The resulting image, now deeply etched into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant image serves as a humbling reminder of the fragility and interconnectedness of our planet, underscoring the imperative to cherish and protect our world. A message that continues to resonate powerfully with people around the globe. Voyager 1's epic journey through the cosmos led it to encounter two of the most enigmatic and majestic celestial bodies in our solar system, Jupiter and Saturn. These monumental encounters provided a treasure trove of scientific data and imagery, fundamentally reshaping our understanding of these gas giants. Jupiter, the largest planet in our solar system, beckoned Voyager 1 with its beguiling mysteries. In March 1979, the spacecraft conducted a close flyby of this colossal giant, granting humanity its first intimate glimpse of the planet's immense scale and complexity. As Voyager 1 ventured closer, it unveiled a tapestry of astounding discoveries. One of the most captivating being the confirmation of Jupiter's intricate ring system. Before Voyager 1's arrival, these faint rings were only a hypothesis, but the spacecraft's keen instruments provided definitive evidence of their existence. Composed of fine, dark particles, these delicate rings encircle Jupiter in an ethereal fashion. The images captured by Voyager 1 offered an entrancing perspective on this subtle feature, captivating the world with their delicate beauty and adding a new dimension to our cosmic knowledge. Another remarkable revelation from Voyager 1's encounter with Jupiter was the unveiling of intricate weather patterns and tempestuous storms on the gas giant's surface. Among these tempests, the most iconic was the Great Red Spot, a colossal storm that has raged for centuries. Voyager 1's imagery of this mammoth tempest not only illuminated the storm's complex structure and dynamic behavior, but also ignited the public's fascination with Jupiter's tumultuous atmosphere. Furthermore, Voyager 1's instruments detected Jupiter's powerful magnetosphere, a colossal magnetic field that dwarfs Earth's own magnetic envelope. This groundbreaking discovery provided crucial insights into the planet's magnetic dynamo and shed light on how this immense magnetic field interacts with its retinue of moons, influencing their environments and contributing to the complex space weather around Jupiter. Following its momentous encounter with Jupiter, Voyager 1 continued its epic odyssey toward Saturn, the majestic ringed planet. In November 1980, the spacecraft made its closest approach to this cosmic wonder, offering humanity an intimate view of Saturn's stunning rings and captivating moons. The detailed images and data collected unveiled previously unseen features of the ring's delicate structure and composition, as well as the diverse geology and atmospheres of Saturn's many moons. One of Voyager 1's most iconic contributions to human perspective came in 1990 with the celebrated pale blue dot image. The esteemed astronomer Carl Sagan championed a visionary idea. He implored the spacecraft to pivot its cameras and turn its lens back toward Earth. This image immortalized our planet as a tiny, fragile speck suspended in the vastness of space, inspiring reflection on our place in the cosmos and a renewed commitment to safeguarding our shared home. The resulting image, now etched deeply into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant and humbling image serves as a powerful reminder of the fragility, vulnerability, and profound interconnectedness of our planet within the boundless expanse of the universe. It underscores the urgent imperative to cherish, protect, and preserve our delicate home, a message that continues to resonate with people from all corners of the globe, inspiring reflection on our shared responsibility to safeguard life on Earth. While Voyager 1's extraordinary odyssey primarily focused on the majestic gas giants Jupiter and Saturn, its twin spacecraft, Voyager 2, embarked on a distinct and equally remarkable trajectory. Voyager 2 was destined to explore the enigmatic ice giants of our solar system, Uranus and Neptune, planets shrouded in mystery and complexity presenting a fresh array of cosmic enigmas for scientists and humanity to unravel. Uranus, the seventh planet from the Sun, is a celestial enigma for many reasons, not least of which is its extraordinary rotation. Unlike any other planet in our solar system, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation is believed to be the aftermath of a colossal and cataclysmic collision with a massive celestial object in the distant past, which drastically altered the planet's spin. This tilt results in extreme seasonal variations lasting over decades, offering a unique glimpse into planetary dynamics that differ greatly from those of Earth and its planetary neighbors. Despite its unusual tilt and mysterious origins, Uranus remains a captivating and fascinating world. It is approximately 4 times the diameter of Earth and boasts a cold, icy atmosphere composed mainly of hydrogen, helium, and methane, giving it a characteristic blue-green hue. Voyager 2's historic flyby of Uranus in January 1986 marked a momentous milestone in space exploration. For the first time, humanity received detailed images and comprehensive scientific data of this distant ice giant, expanding our knowledge far beyond previous telescopic observations. Among the many groundbreaking discoveries during Voyager 2's encounter was the revelation that Uranus possesses a complex system of rings, a surprising finding since rings were once thought to be unique to Saturn. Voyager 2 revealed that these rings consist of dark, narrow bands composed of tiny particles and debris orbiting the planet, hinting at dynamic processes within Uranus's gravitational influence. In addition to its rings, Voyager 2 discovered 10 new moons orbiting Uranus, each with its own unique characteristics and geological histories. The spacecraft's instruments also provided valuable insights into the planet's atmosphere, uncovering high-speed winds and unexpected temperature variations that challenged existing models of planetary atmospheres. These findings offered a new window into the workings of ice giants, enriching our understanding of planetary formation and behavior in the outer solar system. Voyager 2's journey did not end with Uranus. It continued onward to Neptune, the outermost planet in our solar system, arriving in August 1989. Neptune, with its striking deep blue color and fierce weather systems, presented yet another frontier of exploration and discovery. The data and images sent back by Voyager 2 from Neptune's vicinity revealed powerful storms, supersonic winds, and a moon with active geysers. An astounding discovery that further deepened our appreciation for the dynamic complexity of these distant worlds. Together, the twin Voyager spacecraft have revolutionized our understanding of the solar system's outer realms. Their pioneering missions, spanning more than 4 decades, have transformed once faint and distant dots in the night sky into vividly detailed worlds, full of mystery and wonder. These missions continue to inspire generations of scientists, dreamers, and explorers, reminding us that even at the very edges of human reach, the universe holds countless secrets, enigmatic, sideways rotating giant. Voyager 2's interstellar voyage did not end at Uranus. It pressed onward, journeying even farther to reach Neptune, the 8th and most distant known planet from the Sun. Neptune, with its frigid temperatures and vibrant azure hue, remains a haunting symbol of the solar system's outer frontier. This distinct blue coloration is due to the high concentration of methane in its atmosphere, which absorbs red light and reflects the blue. In August 1989, Voyager 2 conducted a historic flyby of Neptune, marking the first, and so far only, close encounter with this distant world. The images and data transmitted back to Earth during this flyby were nothing short of revolutionary. Voyager 2 unveiled a planet with a surprisingly dynamic atmosphere, teeming with violent storms and fierce winds, the fastest sustained winds recorded in the solar system, reaching speeds of over 2,000 kilometers per hour, about 1,200 miles per hour. Among Neptune's most notable atmospheric features was the discovery of the Great Dark Spot, a colossal storm system reminiscent of Jupiter's famous Great Red Spot. However, unlike its Jovian counterpart, the Great Dark Spot proved to be ephemeral. It mysteriously vanished in later observations, raising questions about the atmospheric dynamics of Neptune and the transient nature of its weather system. Perhaps one of the most astonishing revelations from Voyager 2's Neptune encounter was the discovery of the planet's largest moon, Triton, to be an exceptional celestial body that defied expectations. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of Neptune's rotation, a rare trait that strongly suggests Triton is a captured object, possibly a former Kuiper Belt object that was gravitationally ensnared by Neptune in the distant past. Triton's surface was revealed to be a frozen yet geologically active world, exhibiting nitrogen geysers erupting from beneath its icy crust, a phenomenon never before observed on a celestial body so distant from the Sun. This cryovolcanic activity indicated that Triton, despite its remoteness and frigid temperatures, harbors internal heat and dynamic processes beneath its surface. Voyager 2's images showed a landscape marked by frozen plains, ridges, and sparsely cratered terrain, suggesting a young and possibly evolving surface. These groundbreaking discoveries at Neptune and Triton not only captivated the global scientific community, but also sparked the imaginations of people around the world. The Voyager 2 mission demonstrated the boundless potential of human curiosity and ingenuity, reminding us that even the most remote and mysterious corners of our solar system can be brought into the realm of human understanding. Voyager 2's historic flybys of Uranus and Neptune marked the end of humanity's first grand tour of the outer planets, a monumental chapter in the annals of space exploration. Yet, like its twin Voyager 1, Voyager 2 continues to voyage beyond the known, transmitting faint whispers of data from the edge of interstellar space, ensuring that its legacy endures not just in scientific discovery, but in the shared human spirit of exploration. Triton, the largest moon of Neptune, emerged as one of the most fascinating and enigmatic celestial bodies encountered during Voyager 2's interplanetary odyssey. The spacecraft's imagery revealed a world brimming with activity, despite its remote location and frigid climate. Among Triton's most extraordinary features were geysers that erupted from beneath its icy surface, spewing nitrogen gas high into the moon's thin atmosphere. These geysers created vast plumes that extended kilometers above the surface, where the nitrogen would condense into snow-like particles and gently settle back to the ground, sculpting a surreal and alien landscape of frost and ice. This striking phenomenon was unlike anything previously observed in the solar system, offering profound insights into cryovolcanism, the eruption of volatile substances like water, ammonia, or methane, rather than molten rock. Triton's surface, relatively young and sparsely cratered, hinted at a geologically active history, defying expectations for a moon so far from the Sun. Perhaps even more puzzling was Triton's retrograde orbit. it revolves around Neptune in the direction opposite to the planet's rotation. This uncommon trait strongly suggests that Triton did not form alongside Neptune, but was instead a captured object, likely originating from the Kuiper belt. Its gravitational capture would have disrupted Neptune's original satellite system and left Triton locked in a stable but unusual orbital dance, one that continues to intrigue astronomers to this day. Voyager 2's encounters with Uranus and Neptune remain unparalleled achievements in the history of space exploration. To this day, no other spacecraft has visited these distant ice giants, making Voyager 2's observations and data collection an irreplaceable scientific treasure. The trove of information gathered during these historic flybys continues to fuel research and hypotheses, offering glimpses into the atmospheric dynamics, magnetic fields, ring systems, and unique satellite compositions of these mysterious worlds. While Voyager 2 was delving into the secrets of the outer planets, its twin, Voyager 1, was forging an even more audacious path, a journey that would take it beyond the boundaries of the solar system and into interstellar space. This transition, which occurred in August 2012, marked a profound and historic milestone for humanity. For the first time, a human-made object had crossed the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1's entry into interstellar space did not signify the end of its mission, but rather the beginning of a new chapter. As it continues its voyage through the vast and silent reaches of the cosmos, it carries with it not only scientific instruments, but also a symbolic message from Earth, etched in the form of the Golden Record, a phonograph disc containing sounds, music, and greetings from our planet. Now billions of miles from Earth, Voyager 1 operates in a realm beyond the Sun's influence, where the environment is dominated by particles, fields, and forces that originate from other stars. Its instruments, though fewer in number now, continue to return invaluable data about the nature of interstellar space, helping scientists to understand the shape and boundary of the heliosphere and the conditions in the space between the stars. The enduring journey of the Voyager spacecraft, Voyager 1, venturing outward into the galaxy, and Voyager 2, providing the only close-up views of Uranus and Neptune, remains one of the most ambitious and successful missions in the history of space science. They have not only expanded the boundaries of human knowledge, but have also inspired generations to look upward and dream of what lies beyond, gathered groundbreaking data that challenged earlier assumptions and reshaped our understanding of this mysterious frontier. Rather than a simple comet-like structure with a long tail trailing away from the Sun, Voyager 1's measurements suggested that the heliopause is more complex, possibly a distorted bubble-like shape influenced by both the solar wind from within and interstellar forces from beyond. As Voyager 1 crossed this boundary in 2012, it recorded a sudden and lasting drop in solar particles, while simultaneously detecting a surge in galactic cosmic rays, energetic particles that originate from supernovae and other powerful cosmic phenomena far outside our solar system. This was the smoking gun, clear empirical evidence that the spacecraft had exited the heliosphere and entered the vast ocean of interstellar space. Within this realm, Voyager 1's instruments continued to function, albeit in a limited capacity due to the fading power supply and increasing distance. Even so, its plasma wave subsystem detected a persistent background hum, long, low-frequency vibrations in the plasma of interstellar space. This discovery provided an unprecedented glimpse into the density and behavior of particles between the stars, and demonstrated that the void of space is, in fact, filled with subtle and dynamic forces. Voyager 1's ongoing mission in interstellar space is a testament to both technological resilience and scientific ambition. It represents the first time humans have been able to directly measure the environment of interstellar space, rather than relying solely on telescopes or theoretical models. The data sent back by Voyager 1 continues to challenge assumptions and refine our models of how the Sun interacts with the galaxy around it. As it sails farther into the unknown, Voyager 1 is also pushing the limits of communication. Its faint signals traveling at the speed of light now take over 22 hours to reach Earth. Each byte of data is a time capsule, whispering stories from the edge of the solar system to a waiting world. Despite being over 46 years old, the spacecraft continues to surprise. In recent years, engineers have performed innovative workarounds to keep it operational, including rerouting functions through backup systems. These efforts ensure that even in its twilight years, Voyager 1 remains a pioneer, a silent emissary of Earth drifting among the stars. Its journey into interstellar space is not just a scientific achievement, but a symbolic one. Voyager 1 carries the golden record, a carefully curated message intended for any intelligent life that might one day encounter it. Engraved with greetings in 55 languages, music from cultures across the Earth, and images depicting life on our planet, the golden record serves as humanity's cosmic calling card, a whisper to the universe saying, "We were here, we reached this far, and we are curious." Voyager 1 is now far beyond the planets, beyond the influence of our star, continuing its voyage in the silence of deep space. It is alone, yet never forgotten. Its legacy etched into history, its mission ongoing, and its story inspiring countless new explorers to reach for the stars. These observations from Voyager 1 provided a transformative understanding of the heliopause and its complex relationship with the galactic environment. Prior to Voyager's journey, much of what scientists knew about the heliosphere was theoretical, based on models, simulations, and indirect evidence. But as Voyager 1 approached and eventually crossed the heliopause, it delivered empirical measurements that revolutionized the field. One of the most unexpected discoveries was the behavior of the magnetic field at the boundary. Scientists had expected a sharp shift in the direction of the magnetic field lines as Voyager 1 transitioned from the Sun's influence to the interstellar medium. However, what they observed was a subtle and unexpected continuity. The magnetic field beyond the heliopods remained aligned in a way that puzzled researchers. This anomaly suggested that the heliosphere might not be as sharply defined or as neatly contained as once imagined. Instead, it could be intertwined or blended with interstellar forces in ways that challenge our understanding of the boundary between solar and galactic domains. These deviations hinted at previously unknown interactions between the solar wind and the interstellar magnetic field, painting a far more dynamic and fluid picture of the Sun's outermost frontier. In addition to its findings on magnetic fields, Voyager 1 also measured plasma density in interstellar space. Unlike within the solar system, where plasma is sparse and influenced by solar activity, the interstellar medium was found to be denser, yet cooler and more stable. This provided critical data that helped astronomers refine their understanding of the material that fills the vast regions between star systems. Voyager 1's traversal into and beyond the heliopause did more than just expand the scientific boundaries of astrophysics. It redefined the scale of our solar system. What was once thought to end at the orbit of Pluto, or perhaps Neptune, was now clearly shown to extend tens of billions of kilometers farther. Enveloped in a vast and shifting magnetic bubble, these findings are not merely academic. They have profound implications for future missions and our long-term aspirations for space travel. Understanding the heliosphere structure is essential for developing technologies that could one day protect human explorers from cosmic radiation as we venture further from Earth. It also helps in mapping the interstellar environment that any spacecraft, robotic or crewed, would encounter as it journeys to the stars. In essence, Voyager 1's study of the heliosphere turned a once theoretical concept into a tangible and measurable structure, revealing it as a living, breathing force field that protects and defines the domain of our Sun. And while many questions remain about its shape, its interaction with the galaxy, and how it evolves over time, Voyager 1 laid the first real footprints on this invisible frontier. It's a testament to human curiosity and engineering that a spacecraft launched in 1977 continues to inform us decades later about regions of space we had never directly touched before. The mission of Voyager 1 not only broadened our understanding of the heliosphere, but also reminded us that exploration, no matter how distant or difficult, brings us closer to the truth of our place in the cosmos. These contrasting environments encountered by Voyager 1 and Voyager 2 as they crossed the heliopause added profound depth to our understanding of interstellar space. Although both spacecraft pierced the boundary that separates the Sun's protective bubble from the galaxy beyond, the variations in local space weather, magnetic field intensity, and particle density between their paths suggested that interstellar space is not uniform. It is a complex and evolving landscape, shaped by both local and galactic forces. Voyager 2's instruments, still fully operational at the time of its heliopause crossing, recorded direct plasma measurements, something Voyager 1 could not do initially due to a malfunction in its plasma instrument. This allowed Voyager 2 to directly confirm the dramatic rise in plasma density beyond the heliopause, complementing the data Voyager 1 had previously inferred using its cosmic ray and magnetic sensors. This corroboration between two different observational methods provided compelling evidence for a denser interstellar medium just outside our solar system. Moreover, the turbulence Voyager 2 encountered, manifested as fluctuating magnetic fields and wave-like plasma interactions, indicated a more chaotic boundary layer. Scientists hypothesize that this may be due to differences in solar wind pressure or local interstellar cloud structures that distort the heliosphere's edge. In contrast, Voyager 1's path appeared to be through a calmer, more sensitive this frontier is to cosmic condition. Together, these findings from both spacecraft are enabling scientists to create the first three-dimensional models of the heliosphere's outer boundary, which help illustrate its shape, behavior, and interaction with the galaxy. These models are crucial not only for understanding our own solar environment, but also for contextualizing the protective magnetic bubbles that might surround other stars, possibly shielding exoplanets from harmful radiation and influencing their potential to host life. In essence, Voyager 1 and Voyager 2, though launched within weeks of each other, have become dual ambassadors to the galaxy, each offering a distinctive lens on the final frontier of our solar system. Their separate experiences highlight that the edge of our solar system is not a fixed wall, but a living, breathing boundary, shaped by the solar wind's strength, the interstellar medium's density, and galactic magnetic fields that we are only beginning to understand. As Voyager 2 continues its journey through this turbulent interstellar zone, it adds more layers to the grand narrative begun by its twin, Together, they are charting a realm never before visited by humankind. And in doing so, they remind us that even at the edges of our influence, human curiosity and ingenuity still thrive. Reaching out into the unknown, guided by the faint whispers of data traveling billions of kilometers back to Earth, journey marks both a triumph of engineering and a poignant reminder of the finite nature of even our most enduring creations. Now well over 46 years since its launch, Voyager 1 continues to drift deeper into the uncharted sea of interstellar space, carrying with it the legacy of Earth's first true attempt to reach beyond the confines of the Sun's domain. Yet, as the spacecraft travels ever farther, it faces increasing challenges. Its power supply, generated by radioisotope thermoelectric generators, RTGs, is gradually weakening. As of now, NASA engineers have been shutting down non-essential systems to conserve energy and extend the mission's lifespan. Sometime in the late 2020s or early 2030s, Voyager 1 will likely go silent, as its power becomes insufficient to sustain even the low-energy communications that still reach Earth today. Despite this inevitable silence, the spacecraft will not stop traveling. Long after it can no longer send signals or power its instruments, Voyager 1 will continue coasting through the Milky Way galaxy, a silent sentinel bearing the golden record, waiting for a distant intelligence, if such an intelligence exists, to encounter it. This golden record, painstakingly curated by a team led by Carl Sagan, includes readings in 55 languages, music from a wide range of cultures and eras, from Bach and Beethoven to traditional songs from Japan, Senegal, and Peru. Images depicting life on Earth, human anatomy, architecture, DNA structures, and the planet's ecosystems. Sounds of Earth, including the laughter of a child, the roar of the ocean, thunder, and the chirping of birds. These records serve as a kind of cosmic message in a bottle, not with the hope of rescue, but as a declaration: we were here. We reached for the stars. We tried to understand the universe and ourselves. In this way, Voyager 1 and Voyager 2 have transcended their original scientific missions. They have become monuments of human creativity and persistence, testaments to a civilization that dared to send its voice into the dark with no guarantee of reply. They represent an act of faith in the future, a belief that knowledge, wonder, and the desire to explore are enduring parts of what it means to be human. As we gaze toward the heavens, tracking the faint signals from these emissaries, we are reminded that our reach has already extended beyond the solar system, and that even in the cold emptiness of space, our story continues. The Voyager mission teaches us that the journey itself, filled with discovery, wonder, and enduring hope, is as important as the destination. Voyager 1's incredible journey has reignited the world's fascination with this fearless spacecraft after more than 4 decades of exploration. Voyager 1 has traveled far beyond our solar system, venturing deep into interstellar space. It has crossed the heliopause, the boundary where the sun's influence fades, and now drifts through a vast, uncharted region of the galaxy. In August 2022, Voyager 1 sent a mysterious message back to Earth, one that captured the imagination of scientists and space fans everywhere. Amid streams of data and telemetry, researchers detected a strange anomaly, an object of unknown origin and makeup. Tentatively named the cosmic enigma, this object is unlike anything ever encountered in the history of space exploration. What makes the cosmic enigma so puzzling? It emits faint, irregular signals that don't match any known natural celestial phenomena. Even more intriguing, its path through space seems deliberate, as if it's following a specific course through the cosmos. This discovery raises deep and fascinating questions. Where did this object come from? Who or what created it? And what might its intentions be? Scientists and astronomers around the world have been meticulously analyzing the data sent by Voyager 1, determined to unlock the secrets of the mysterious cosmic enigma. Could this baffling object be a remnant of an advanced extraterrestrial civilization, or perhaps a probe launched from a distant corner of the galaxy? Alternatively, might it be an entirely new and unknown cosmic phenomenon? The discovery has ignited a wave of speculation and debate, bringing together experts from diverse fields who are collaborating to unravel the enigma's true nature. One leading theory suggests that the cosmic enigma could be an ancient relic from a long-lost civilization, a probe dispatched eons ago, its original mission veiled in the mists of time. Whether its purpose was scientific, exploratory, or something beyond our imagination remains an intriguing mystery. On the other hand, some scientists propose that this object might be a natural celestial phenomenon, with properties that challenge our current understanding of astrophysics. This possibility reminds us of the universe's immense complexity and the vast diversity of cosmic phenomena still waiting to be discovered. It highlights how much we have yet to learn and how little of the universe's secrets we have uncovered. The detection of the cosmic enigma underscores the critical importance of continued space exploration. It calls for humanity to push further into the cosmos, to embrace the unknown, and to expand our cosmic reach. The universe is a vast, mysterious frontier, filled with wonders and enigmas that inspire awe and curiosity. As Voyager 1 continues its solitary voyage through interstellar space, carrying with it the mystery of the cosmic enigma, humanity stands on the brink of new discovery. This spacecraft has become Earth's ambassador to the stars, a shining symbol of our insatiable curiosity and unyielding desire to explore. Voyager 1's odyssey, spanning over 4 decades, has fundamentally reshaped our understanding of the universe. It continues to inspire generations of scientists, dreamers, and stargazers alike. As we ponder the mysteries of the cosmic enigma and the endless possibilities it represents, we are reminded that the cosmos is a vast, wondrous, and ever-evolving realm. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? With its indomitable spirit and enduring mission, Voyager 1 carries our hopes and dreams as it forges onward into the cosmic unknown. The story of Voyager 1 is a testament to the enduring human spirit of exploration, curiosity, and the relentless quest for knowledge. It transcends time and space, reminding us of our place in the universe and the boundless wonders awaiting us in the cosmic expanse. The enigma of the cosmic enigma serves as a poignant reminder that the universe is filled with mysteries yet to be unraveled. It invites us to continue our cosmic journey with wonder and humility, ever eager to explore the depths of the unknown. Voyager 1, humanity's cosmic emissary, continues to inspire us to reach for the stars and embrace the infinite possibilities that lie beyond.